Unit 6 is on Newton's laws. Have you guys ever heard of any of Newton's laws? What do you got, Elias?
Isn't Newton's laws isn't the guy that founded Newton's laws?
He was.
Isn't gravity, like the guy was sitting under the tree and like the apple fell?
Yeah, that's the legend of the apple hitting him in the head.
That's gravity.
Yes, Caitlin? Newton is a unit. What is it a unit for? For what? For unit 6. We've used Newton before.
Yeah.
Tori, do you remember?
It's for pressure and stuff.
It's not for pressure, but something related to pressure.
I swear to God.
No? Yep, Jen? Force. It's just in general force. And when you said gravity, you said gravitational force, that's where we used it. But in general, it's for all forces. Newtons are
When we talked about newtons per kilogram.
Yes, newtons per kilogram, that was the gravitational field strength. Exactly, so that was a force per mass. Awesome. So have you ever heard of any of Newton's laws of motion? Jen?
Every action has its equal opposite, yeah.
Okay, so there's every action has an equal and opposite reaction. That's Newton's third law.
Have we talked about this before?
I don't know, not in this class. It probably in previous classes.
It's slowly refreshing.
Yeah, and then what about the other two? If that was Newton's third, there's probably a first and a second. That'd be weird if he just said, this is my third law.
Maybe you just likes threes.
Maybe. Okay, but I'll give it away. There's a first and a second. What you got? Any other, ever heard of things for Newton's laws? Caitlin. How things fall? Okay, and that's probably closest to Newton's second law, which is a relationship between acceleration, net force, and mass. We're going to be spending a lot of time on that in this unit. Elias?
Isn't one of Newton's laws everything that goes out must come down? Or something
No,
like
that is not a law.
Oh, I thought.
That is, everything that goes up must come down is just, that's just gravity. That's not really a law. Aspen, what you got? Guys, I can't hear. Not about energy. No, you're thinking about like energy cannot be created or destroyed. That's just conservation of energy. That's not Newton's laws. What do you got?
Oh, so, like this is his first, second, and third.
Are you looking up stuff?
Yeah.
What you got? Tell me about Newton's first law.
It says, in the first law, an object.
Hold on. Before you read it, I'm going to anticipate everybody in the classroom going, oh yeah. Okay, go ahead.
In the first law, an object will not change its motion unless the force acts on it.
Oh, yeah, I remember that.
See what I'm saying? An object at rest will stay at rest. An object in motion will stay in motion. Does that ring a bell? All right. That's Newton's first law. Okay. So that's what we're going to be doing this unit. We're going to be talking about those three laws, but we're mostly going to be focusing on the second law. But today we are going to do all about the first law. So to talk about sort of why we're doing this, let's think about what we just did. Last unit, what did we do?
2 days ago.
Yeah. What kinds of things did you do for last unit? You graphed. What kinds of things did you graph?
Find slope. Find slope.
Okay. You found a slope.
Oh, position versus
Position
velocity.
versus time, velocity versus
Ah.
time, acceleration versus time.
Yes. You did things with X, V, and A, right? What we did, yeah, but I'm trying to make a point here. So last unit, we described motion. You looked around at stuff and you said, hey, where is it? How fast is it going? And how fast is it, and how is that speed changing or velocity changing? Okay? That X, V, and A described the motion. Does that make sense, what I mean? Okay? What this unit is going to do is we're going to ask the unit, we're going to ask the question, why? Why is it moving like that? What made it do that? Or did it need something to make it do that? Okay? Yes, Tori?
Here's one fun fact. Everything is perpetually in motion because this is constantly rotating around the sun, so we're always moving, we're perpetually moving.
I agree, and that's all about reference frames.
We're moving ourselves.
Yeah. So we could talk more about reference frames, which is what you're talking about. But right now, I want to make sure that we get,
Wasn't this in the test or in the quizzes? Like this
so
question?
we haven't done anything yet. Like, that, I just said that was last unit, was X, V, and A. But do you,
never mind. I
right,
don't
but
think
this
it's a-
unit, we're saying why. Why do things move the way they're moving? Okay? So, Amanda, you okay? You need to do some jumping jacks? Sometimes people get tired after lunch, right? Okay, yes, Tori.
For anything to move, there has to be a force acting on it.
I am sorry, that statement is incorrect.
But it is
Ooh.
true.
It is incorrect. So therefore, it is not true.
Forces do have something to do with motion.
I agree. That I can agree with. But there's a subtlety in what you said. So that's what we're going to explore.
Show you.
I am. Whoever is scooching whatever needs to stop. Okay. So we are going to look at 4 different situations. We're going to look at a book on a table, just chilling there. Okay? We're going to look at a ball falling. We're going to look at a bowling ball moving across the floor. And finally, I will push a book across the table and it will slow down. Okay. Before we talk about why any of it's happening, we're going to just observe the motion. Talk about the X, V, and A of it all. All right? So, here we go. There is a book. Talk to me. What do you...
It's a physics book.
It is a physics book. Of course it's a physics book. What words could you use to describe what you're seeing right now? It's not moving. Okay, I like it. Not. Okay, good. You could say at rest. You could say not moving.
Although it is in motion.
So it's at rest with respect to the room. We're keeping this as our reference frame. Okay?
Yeah.
So it's at rest, not moving. Is it changing its motion at all? No, right? So there's no,
Yeah.
what's that?
Also, gravity is pulling on the book.
Right now,
But the
I'm not
table is
asking,
pushing up on it.
Tori, you're gonna need to let me lead the group, okay? Right now, we're not talking about gravity. Right now, I'm just asking, so it's important to listen to what I'm asking for. What do you see? Do you see gravity? I don't see gravity. You're right, gravity is acting on the book, and that's what we're gonna talk about next. But the first thing I wanna do is talk about what we see, what we can really see in terms of the description. So, no change in motion. Okay, cool. Here's a ball. So now we're gonna do number 2. I'm gonna drop a ball. I want you to focus on just after the ball leaves my hand, but before it hits the ground. Okay?
Wait, what?
After it leaves my hand, but before it hit the ground.
It's falling.
So yeah, let's hear some words. Falling. What else?
We just said that.
Yes, Tori?
Gravity
accelerating.
sucked it off.
It's accelerating. Okay.
Gravity did it.
You're right, gravity did do it, but we're trying to focus right now on what we see. Why do you know it's accelerating? Yeah, Danielle?
Because it fell down quickly and then went back up.
Okay, but we're not focusing on what the ground did though. But it went down quickly and it got faster and faster as it fell, right?
I think our class has an obsession with gravity.
That's fine. You're gonna really love the next thing we're doing. We're gonna talk about gravity a lot. So, does everybody see that it's sped up? Everybody like feel that in their soul? Okay. So, right, it's speeding up. That means that it's changing velocity, right?
Yep.
Okay. Everybody agree? Awesome. All right, next thing we're going to do is we have a bowling ball. Hold on one second. Okay, so the next thing we're going to do is we're going to take a bowling ball. Actually, Miss Peters, would you like to do the honors?
Bowling ball?
Of course there's a bowling ball. This is a physics class.
Classroom.
Duh. Talk to me about what the motion of that bowling ball looked like to you. Did it speed up? It was like freakishly constant velocity.
Yeah, that's gonna be
Right?
bowling alley, right?
Pretty awesome. So it was moving at a constant velocity.
That also means constant speed.
In this case, constant velocity is constant speed in a straight line. That's exactly what constant velocity means. Okay? So, constant velocity. Are there any other descripting, that's a word now? No. XVA. Are there any of those ideas that we can also apply here? If it's constant velocity, is that something else true?
No acceleration.
Yes, good job. No acceleration. Okay, now, one more. Here's a book. And what happened? I'll do it again.
Oh, that was too quick.
Oh, I'll do it again.
It's moving.
It's moving. So I want you to focus on what happens after it leaves my hand. It slowed down. Huh, cool.
Friction.
Ooh. Slowed down. We will get to friction. I have a quick question about friction, though. Do you remember when you learned about friction?
Like when
No. No is probably the answer. That is a normal... What? Sorry, go ahead, Ms. Peters. No. I'm saying you've grown up with this idea of friction. That's a normal idea, right?
Rubbing your head on the carpet or something?
Yes, that's
Yeah.
static charging by friction. So what's important to realize about friction is the fact that you kind of can't imagine a world without it. And you know that word, friction, okay? I want you to remember that when we start talking about Galileo in a little bit, okay? I know, you're excited about Galileo? Cool. So, all right, so the book slowed down. What other words can we use?
negative acceleration.
Ooh, so we can say it was definitely accelerating. And the sign of that acceleration was the opposite of our velocity. Absolutely. It's accelerating. If I said, yes, it's slowing down. If I said that it changed velocity, would you be okay with that? Yeah? Okay, cool. So, changed,
In situations 2 through 4,
hold, changed, velocity. Okay, go ahead, Tori.
in all examples, say example 1, there was a change in position.
Okay, I agree. All right, so we've described the motion. Now I want to talk a little bit more about some of the forces that these things are experiencing. What's that? You're allergic to physics? Yeah, sometimes on your tests I think you're allergic to units. But anyway. All right, talk to me about this book on the table. What forces is that book experiencing? Gravity. Gesundheit.
Oh, isn't there another one that like pulls you up? I remember learning something about that because if it was just gravity, you would sink all the way down. So there's another force that helps you pull you up.
Yes, Caitlin.
What's holding it up?
The table. The table. We don't even need fancy words for it, right? The table is pushing it up. Does everybody see that?
Yeah.
Nice. Okay, let's keep going. The ball. Oh my goodness, what is happening sneeze-wise? So many sneezels. Okay, what you got, Tori?
The ball had gravity affecting it as well.
Yes. Okay. So remember, I'm writing gravity, but that's also weight. Same thing, right?
Also,
Yes.
with inertia, the inertia of a big rock is like kicking, it hurts.
Yep.
So, and when the book is on the table, it's pushing on the table as much as gravity is pulling on it. Or the table pushing on, the book and the table are pushing against each other with the same amount of force.
I agree.
Like a person pushing on a wall.
Yes, that is exactly right. And what you're talking about right there is Newton's third law. Good job.
I want to be inside Tori's brain.
I know, Tori has an awesome brain. Okay, so are we good on the ball? Anything else? Anything else having a force on the ball? I did not. Yeah, this was after it left my hand. I also just dropped it, but it's after I left my hand. Anything else? We're not in a situation where air resistance is going to be an issue, so I think we can just say that that's enough. All right, what about number 3? What about the bowling ball?
As it rolled on the ground, there was friction.
How do you know that?
Friction, when things rub against each other, friction helps and slows them down.
Yeah, it's what's interesting about rolling. Rolling's really hard. Like, wait till my AP class to do rolling. You actually, it's not the kind of friction where things are rubbing against each other. It's the static friction. So the actual bottom of the ball is at rest with respect to the ground. This is, you don't need to know what I'm talking about right now. My point is friction is not a force here that we need to discuss in this discussion because it doesn't do work on the ball. Don't worry about it, just trust me. Okay, but I'm happy to talk to you about it later. So we're ignoring friction because it's rolling. What else? This bowling ball. Gesundheit. What is happening in my room? Everybody's sneezing.
Gravity is a habit.
Gravity. Oh my gosh, you guys, have you noticed that the answer is always gravity? Like, it's always gravity. Okay, but there's more. There's more. There's more. What else? This bowling ball is on what? The floor. Do you think the floor is pushing it? Pushing up, perhaps?
The floor is pushing it up.
It is. The floor is pushing it up. All right, awesome. Now, last one. We've got the book slid across the table.
That's got a bit of friction.
That's got some friction that we can talk about. By the way, it also has gravity and
The table.
the table. Okay. Let's take a moment here and look at these 4 different situations.
And the only one situation doesn't have something pushing up on what's being on the item.
Okay?
There's the table and 5 in 1 and 4 with the book, and 4 with the bowling ball.
Yes.
But 2, it fell down, but when it hit the floor, its acceleration caused it to bounce back up.
Okay, so we're not focusing on what's happening with the floor. So here, let me lead the class, okay? Have you guys ever heard the term balanced and unbalanced forces? Yeah? Okay. Go ahead, Tori.
Balanced forces is when there's say when the book is person pushing on a wall.
That one's trickier because
You push on the wall with as much force as the wall is pushing.
yeah, but that's a Newton's third law argument. A balanced force. So imagine I'm standing here and someone pulls me this way, someone pulls me this way, right? Can you imagine if they pulled the same? It would be balanced, right? Like a tug of war, right? But if these people won, right, and these were weaklings, okay, we would have unbalanced. Does that make sense when I'm saying balanced and unbalanced?
Yes.
Okay. Now look at this. What do you see? Now that you're thinking about balanced and unbalanced.
Oh.
Yes. That's the sound of learning. Let's hear from some other people. Does anybody else see anything interesting about balanced and unbalanced forces? Do you think that number 1 is balanced or unbalanced? Okay. Do you think number 2 is balanced or unbalanced? Good. Do you think 3 is balanced or unbalanced?
Balanced.
Do you think 4 is balanced or unbalanced?
Unbalanced.
That one's unbalanced. That's a little harder. Because this part got balanced, but this part's not balanced. Okay? So, what did we just say? We just said that 1 and 3 were balanced.
Because there's an equal number of forces.
Not necessarily an equal number. That's not the issue. It's that they were the same size and in opposite directions. Okay? So, the ones on the left were balanced. The ones on the right were unbalanced. Now let's look at their motion and see if we can put this together. Tell me about what you see for the balanced forces.
Bless you.
It's on height.
Wow, lots of sneezes.
I know, so many sneezes. What do you see?
I just realized something.
Go ahead.
In both examples of balance force, there's no acceleration.
Aha! Wow, that was dramatic. Sorry, I did not mean for it to be that dramatic. Well, hopefully that woke people up in case they were sleeping. There is no acceleration, constant velocity, no change in motion means acceleration is 0. Ah, we're putting it together. If it's balanced forces, there's no acceleration. Look over at unbalanced.
Both of them-
What do you see?
Both of them have acceleration.
That's
I don't
right.
have room for this.
You don't have room.
Yeah, I didn't space out my words evenly.
Okay,
It's like
you can,
better.
and you can get this later.
Okay,
I'll put this up.
okay.
Okay? So unbalanced, do you guys see? On the unbalanced side, that's what's causing an acceleration. You feeling okay, Amanda? You need to get up, do some jumping jacks? Do you want me to throw things at you? What do you want?
I'm good.
You good?
Fried her with candy.
What's that?
Fried her with candy without the ranch.
Put her in a sugar crash. Okay. All right. So let's just summarize that real quick. So unbalanced forces and balanced forces. So tell me what you can say about things with unbalanced forces.
One side strong.
One side is stronger. Okay, that's why it's unbalanced. Just wait, Tori. Unbalanced forces. What can we conclude that we just did from the previous page? So it would be in your notes right now. It's accelerating. Thank you. Right? There is a change in velocity, right? There is acceleration. All right, what about balanced forces? Good. So there's no change. And I know that my handwriting is horrible. So if you can't read it, please let me know. No change in velocity. Okay. We could also say acceleration equals 0. We could also call that constant velocity. All of those things are the same. Yeah? And so hopefully now, starting in your brain, you've got constant velocity, acceleration is 0, and now you're adding unbalanced forces. Sorry, just kidding. Balanced forces, my bad. Right, as like a combination. Okay? And just to be really, really specific, a constant velocity, can you describe what that motion looks like? Danielle?
Like it just like keeps going, does it like change?
It's what?
Like it just keeps going.
Yeah, it keeps going in a straight line, right? Like our bowling ball, right? By the way, our book also has a constant velocity. It's just a velocity of 0, right? But if it's moving, then you can say it's at a constant speed. So think about what the speedometer looks like. It's stuck there, right? Constant speed
in a straight line. Okay? How are you feeling about this? It's okay? You get some vigorous nods, or you with me? Okay. Because we're about to ready. We're about to ready?
Yeah,
Oh, yes.
we are.
We are ready to write down Newton's first law. I know you're excited. By the way, just so you know, I'm not the kind of teacher that makes you memorize crap like this. That's stupid. I want you to understand it, but I don't want you to memorize it. But it's important to have written in your notes, okay? Newton's. You got cadence? Newton's first law. Okay, by the way, you'll find out why in a little bit. This is also called the law of inertia, okay? Newton's first law, which is also called the law of inertia, even though we haven't defined inertia yet. Yes, ma'am?
What's that last word?
Inertia, I-N-E-R-T-I-A. All right, here we are. Let's write it out. An object at rest and an object in motion stays at so many words, guys. I'm sorry about this, but we just got to get it down, right? Constant speed in a straight line. And don't worry, I'll pause after this so you can get it down. Unless acted upon by an unbalanced force. So I will pause. What? Yep. So at rest and constant speed in a straight line mean that acceleration is 0. So again, the acceleration is 0 of an object unless there's a reason for it not to be. Okay? So this is why this is such an interesting law. Okay? Galileo, okay, remember I said we were going to talk about Galileo. All right? Galileo did something super cool. He imagined a world without friction and thought, what do objects really want to do if there's no friction? So can you imagine a world without friction real quick? The final frontier. What would happen?
Everything would just slide.
Yeah, could I do this? Could I walk? No. No. Just be like floating. You think I would float? Oh, so gravity's gone too?
You just slide everywhere.
You'd slide.
floating
You wouldn't be able to,
Would people get fat? Or
right? So I was,
Would people
so
get fat if they were just
would people get fat? It's like the movie Wall-E.
Yeah.
That's because they're not,
I'd be
like,
a bowling ball.
that,
I would be the
they're
one
human?
rolling-
I can't believe I'm recording this. Okay,
Miss Ray, I
good.
would be the one rolling around.
In not so many words, that things to keep doing what they're doing. Okay? Things want to keep doing what they are doing. And honestly, the only reason that they change what they're doing is because of forces on them. Okay? And again, the reason that this was so amazing was that literally everything in your life you see like comes to a stop. Right? And it's because of friction. So the fact that he could imagine, first of all, what friction was, because that wasn't like a thing, right? And then say, wow, what if we took it away? Like that's why it was so cool. Okay? So things want to keep doing what they're doing. And this concept of inertia was Galileo's. And that is an object's resistance to a change in motion. And have you ever heard that word before? Inertia?
Yeah.
It's an English word. What does it mean? I don't know. I feel like it's just...
Yeah, put it on Bill Nye.
You heard it on Bill Nye. That's good. Okay. But the English word inertia actually just basically means this. That doesn't always work out in physics, right? Sometimes we have physics words that mean something completely different than English, like work. Remember how work? Remember how we said like work was a very specific physics definition, right? Inertia is basically the same. Okay, so now, in order to really learn this, we need memes. Okay, so mass is a measure. Oh my goodness, that was very squeaky. Of inertia, right? If you have more mass, then you have more resistance to change, right? So the big football players, I don't remember which ones are which. The one, he's running, is he a running back? I don't know. That sounds right, but I don't know. No one's helping me either. You're just watching me flounder. Who's a big dude who's running? Kenny, okay. So when Kenny runs, right, if you have more mass, you have more resistance to change in motion. Like, if an elephant was running straight at you, how could you avoid being hurt? Like, literally, the elephant's coming this way, all you gotta do is this. Right? Because the elephant is like, he's on a path. It's not so easy to move, right? But if a mouse was out to get me, then I'm screwed.
That's way more.
Will you stop with the stuff? All of my students have suggested stepping on the mouse.
Yeah.
That's nasty, people. Okay.
A little blood will hurt.
I think taking it would be the
Okay. Just make sure in your table of friends that you have mass. Does anybody remember what the variable is? It is M. And what are the SI units? Kilograms.
Oh, yeah, I meant to say that.
Sure.
Yeah.
Okay.